Well, thanks a lot, Francesco, for this nice introduction and the invitation to give you a short version of some results that I proved that I did in my PhD thesis. So, as the title of my talk is the singular Weinstein conjecture, and this is joint work with Eva Miranda, which is my supervisor. And at the very last end, there will also be some results that Eva and I am doing in collaboration with Daniel Peralta Sales from IFEMAT in Madrid. And so before starting the talk, let me just give you like a very brief overview of what this talk will be about, because like as most of you know, if we talk about Weinstein conjecture, this is about contact geometry. So where does this enter here in the framework of this Friday Fish seminar? So what we'll do is we'll talk about the generalization of contact structures, and those can be seen as a particular case of Jacobi manifolds, okay? And so what we're interested in is mainly the dynamical aspects of those manifolds, okay? And to give you an idea, like those can be thought as hypersurfaces of some certain kind of Poisson structures, okay? So if I had to say two words where this talk here fits into the setup, would be dynamics on Poisson manifolds, okay? On a very particular kind of Poisson manifold. So this is where this talk should be situated in, okay? And I'll motivate those very particular manifolds by some examples coming from celestial mechanics. Like this is not what people in this audience may be very familiar with. So let me get right into this. So the example that we're considering is the restricted planar circular three-body problem. So the three-body problem consists of three bodies moving into space and being attracted following Newton's second law, okay? So, and here restricted means that one of the three bodies has a negligible mass, and this is here the spacecraft, okay? So we have a primary, secondary, which we'll often call the Earth, the Moon, and we have the spacecraft. And what people classically are interested in is the motion of the spacecraft, or more particular, the periodic orbits of the spacecraft. And so this is what restricted means. And so as the mass, well, as the spacecraft is to be considered of negligible mass, it doesn't interfere with the motion of the primary and the secondary. So those just move following Kepler's law. And what we assume is that they move around circles. So this is where the circular comes into game. And they move around the center of gravity, okay? And then planar means that the motion of the spacecraft is happening in the same plane as the primary and the secondary, okay? And as I told you, we're interested in studying the dynamics of that spacecraft. So first step to do is to write down the Hamiltonian of that spacecraft. So the Hamiltonian is as usually given by kinetic plus potential energy, okay? And this is a time-dependent Hamiltonian because the potential depends on the position of the Earth and of the Moon, which are our two primaries here, okay? And if you'd like to study the level set of this Hamiltonian, this is not good if it's time dependent because it's not a conserved quantity, okay? So what you do instead, because of this spherical symmetry, you go to rotating coordinates, and in those rotating coordinates, this Hamiltonian writes down like this, okay? So you have a time-independent Hamiltonian now, okay? And the price to pay is that it ceases to be the sum of kinetic plus potential energy, but you have some additional term here that can physically be interpreted as the centrifugal force, okay? And this is a Hamiltonian that is well studied. It has 5 critical points, okay? Which are called the Lagrange point, and those are usually ordered as is written here in the slide, okay? And so, as I told you, we're interested in the periodic orbits of that Hamiltonian. And if I had to name two different options to study those, so those would be either at the side of dynamical systems. So I wrote down here perturbative methods. So this is what people may know, for instance, as KEM theory. Okay, but more recently, there's also been the contact topology, or applications of contact topology to this very particular problem. And this is what I'm going to talk about a little bit. Okay, so if you want to talk about contact topology, you need to talk about more precisely the result that is really being applied here is Weinstein conjecture. Okay, so if you have a symplectic manifold and you have a hypersurface in that symplectic manifold, this hypersurface can have many different structures, but one of the ones that can appear is the one of contact manifolds. Okay, and this happens exactly when you have a Liouville vector field. So this is a vector field that expands the symplectic form exponentially. Okay, and if that Liouville vector field is transversed to that hypersurface, this hypersurface is in fact contact with a contact form that is induced by the contraction of the symplectic form with this Liouville vector field. Okay. Moreover, if this hypersurface is a level set of a Hamiltonian, then the dynamics of the Hamiltonian vector field and the Rip vector field, so this is a uniquely defined vector field for this contact form here, are the same up to reparameterization. So studying the Hamiltonian dynamics on that manifold is really studying the Rip dynamics. Okay. Then you have this famous conjecture of Weinstein that tells you that in the closed case, so without boundary compact, this vector field always admits at least one periodic orbit. Okay, and so this is what one would like to apply in the setup of the restricted three-body problem, and this has been done successfully by Albers, Frauenfelder, Kurt, and Paternane. And so what they prove is that if you look at the level set of this Hamiltonian that we had before, for energy smaller than the first critical value, okay, this has three connected components. So you have one connected component where the satellite remains close to Earth, another one where it remains close to the moon, and one where it's far away. And so what they prove is that there exists a Liouville vector field. Okay, so I didn't write down, but this is a Liouville vector field for the standard symplectic form. Okay, that is transversed to the connected component that is the connected component where the satellite stays close to the Earth. Okay, so this immediately implies that this is in fact a contact manifold. So where the contact form is given by this form here. Okay, and this is not good enough because this is not a compact manifold. Okay, so you cannot apply Weinstein conjecture here. Although I should have said that Weinstein conjecture is a conjecture, but it's known in many different cases. So for instance, in dimension 3, it's known to be true that so Weinstein conjecture is solved in dimension 3. Okay, so this is a three-dimensional manifold that is contact, but it's not compact. Okay, because of collision of the satellite with the Earth. Okay, so this is why Weinstein conjecture here doesn't apply, and we cannot say anything about periodic orbits. But the way to solve this somehow is to check that this hypersurface in the cotangent bundle, okay, can in fact be regularized. And this is a very classical thing that people in celestial mechanics know is Moser regularization. Okay, and this manifold can compactify it to RP3, in fact. And this Liouville vector field that we had before can be extended to that setup. Okay, so this means that we have a contact form on that compact manifold, okay, which is three-dimensional. So by the positive result of Weinstein conjecture in dimension 3, you have periodic orbits on the compactification of this hypersurface here. Okay. And so this is very good. So we now know that there's at least one periodic orbit for this energy level set here. Okay, but somehow this is not good. Okay, and this is a little bit what I want to point out during this talk. Okay, because this is not good in the sense that those periodic orbits that we found is not a periodic orbit for our initial system, okay? Because this is, we want to compactify this set here. So this periodic orbit in the initial system may be a periodic orbit that is on the collision set, okay? And we somehow lose control over the localization of this periodic orbit. And this is a little bit what I want to address in this talk. So how can we address this? And our point of view is that we can address this by keeping track of the singularity in the geometric structure, in fact, okay? And so this is where some more general geometric structures than only contact geometry appears, but also, those are in fact a b-symplectic manifold and b-contact manifolds, okay? So this is a little bit the our point of view. So let me briefly tell you where this singularities come from. So for instance, those singularities come from studying the manifold at infinity. Okay, so this is also something that people in celestial mechanics often do, is that they consider the McBee heat change of coordinates to study the manifold at infinity. So this is not a smooth change of coordinates. Okay, it exchanged the origin with infinity. In fact, this is a non-canonical change of coordinates. So the symplectic form that was given initially by dr wedge dpr plus d alpha plus dp alpha, okay, in those new coordinates writes down as -4/x cubed dx wedge d alpha plus dpr wedge dp alpha. Okay, so this is not a smooth symplectic form anymore, but it has some singularities here. And this is what is called a B3 symplectic form. Okay, and this is exactly where we enter the subject of this conference or seminar here, and this is that all of you know that the dual of this, even though this form is not defined at x equal to 0, the dual of this form is gives rise to a Poisson structure that is of course well defined. Okay, so those b-symplectic forms can be seen as a particular case of Poisson structures. Okay, but are more general, of course, than a symplectic structure. And what I told you before is that we're interested in the dynamics of a Hamiltonian vector, of the Hamiltonian vector field on this manifolds here. Okay, so this is a little bit about the global overview of what we're going to do in this talk. Okay, so let me introduce you to BM symplectic and BM contact manifolds. Okay, so as all of you know, like you have different ways of looking at Poisson structures. So this BM symplectic manifold, those can be seen as a particular case of Poisson structures. A different way, more algebraic way, is to look at them as, in fact, symplectic structure modeled over Lie algebroid. Okay, and the Lie algebroid that we're talking about here is the b-cotangent bundle. Okay, and so to define this b-cotangent bundle, the easiest way is to fix a hypersurface. So let us fix a hypersurface Z that is a level set of a function f. Okay, and what we're interested in is the vector fields that are tangent to that hypersurface Z. Okay, this hypersurface Z is called critical set. Okay, and because this is a finitely generated C infinity module, so Swan theorem applies, and it tells you that there exists a bundle such that the sections of this bundle are exactly the vector fields that are tangent to Z. Okay, and this bundle is called the B-tangent bundle, and of course we can take the dual of this bundle and we can consider differential forms by just taking sections of wedges of the dual of that bundle. And the nice thing is that this forms, which are not smooth differential forms, but they have a very easy expression decomposition into smooth forms. Okay, so so the decomposition goes as follows: if you have a B form of degree k, this writes down as alpha wedge d f over f plus beta where F is a form of 1 degree less and a smooth form of 1 degree less, and B is a form of the smooth form of the same degree. Okay, this decomposition here allows us to define an exterior derivative, or extend like the exterior derivative from smooth forms to those B forms by just defining this expression here. Okay, so it's clear that d squared is 0, and that this is really an extension of the exterior derivative to those B forms. And now we have all the ingredients to define b-symplectic and b-contact manifold. So a b-symplectic form on an even dimensional manifold is a B form of degree 2, such that it's closed for this differential that we just defined, and is non-degenerate for that bundle that we had. Okay, and so this non-degeneracy writes down as like omega to the nth power is not 0 for as a section of the maximum wedge of the B tangent bundle. Okay, and in the same way we can define contact forms for this bundle here. So this is a 1 form of 1B form that satisfies this condition here. Okay, so those are extensions of symplectic structures and of contact structures, and a further extension can be obtained by considering higher order singularities. I'm not going into detail about this, but like this is considering higher order singularities. So to give you a global picture of this is the following. So you have symplectic and contact with this link with the relationship that I was mentioning, that hypersurfaces of certain type in symplectic manifolds are contact. Okay, and you have that by considering like this construction that I told you before. You get b-symplectic forms, which is a generalization of symplectic. You get b-contact forms, which is a generalization of contact forms. Okay, and so to really situate all those objects in for the audience here. So those b-symplectic forms are a particular case of Poisson structures, and so another way of seeing those b-contact forms is in fact seeing them as a very particular case of Jacobi structures. So Jacobi structures are further generalization of Poisson manifolds, but those b-contact structures can be seen as a particular case of those as well. Okay, so this is a very sketchy overview of all of this. And as I told you, what we're interested in is the dynamics of those manifolds here. So let me define a unique vector field, which is called the Reb vector field for a given B contact form. Okay, and this is defined by those 2 equations here. So I mean, here we're in dimension 3. Okay, otherwise you should put like a power of n here somehow. Okay, and so to give you 2 examples, you can take R3 with a critical set given by z equals 0. Okay, so you have R2 as a critical set, and you have let's say 2 different contact forms on that manifold. Okay, you have 1 B contact forms, which is given by dz over z plus x dy, and you have 1 other contact form, B contact form, that is given by dx plus y dz over z. Okay, those 2 contact forms are very different because for the first contact form, the Reb vector field is z ddz, and for the other contact form, B contact form, the Reb vector field is given by ddx. Okay, so as a smooth vector field, this Reb vector field that we defined can vanish. This is something that is, of course, not true for the Reb vector field of a contact form. Okay, and then one thing that I would like to point out is, well, I mean, you can of course analyze like the local structure of those, and this is really not what we're going to do here. But one result that I would like to point out is that this relationship that I was mentioning before, that a particular case of critical of hypersurfaces in symplectic manifolds are in fact contact manifolds. This remains true for in the B category. Okay, so if we have a b-symplectic manifold and you have a vector field that satisfies this equation here and that is transversed to a given hypersurface in that manifold here, then this hypersurface admits a B contact structure, and the induced B contact form is given by the contraction of the symplectic form with this vector field. Okay, so this is all I want to talk about the local geometry of those. So let me talk about like the dynamics of BM contact manifolds. So more precisely, of course, like what I mean by this is the dynamics of the Rip vector field associated to those. Okay, so and I mentioned that the Rip vector field of those can vanish. Okay, so as the vanishing of this, as this Rip vector field can vanish, okay, you can ask whether or not there exist plugs. Okay, and well, I mean, for those who don't know what are plugs, plugs are often used to produce counterexamples to conjectures, or to produce counterexamples to existence result of periodic orbits. Okay, so here's the definition of a plug. It looks like a really big definition, but
sorry, can I ask a quick question? You say
sure.
that the Rip vector field can vanish, but can it also, like, as a section of the log tangent bundle, it is non-vanishing?
Exactly, as a section of the log as a section of the log tangent bundle or B tangent bundle, it's not vanishing. There's a smooth vector field is vanishing. Yeah.
Sure. Okay. Thanks.
So, so this definition looks very huge, but it in the heart is very easy. So what you have is a flow box here. Okay, you have like a cylinder here. Okay, and on the boundary of the cylinder, you just have the linear flow going upwards. Okay, the t variable is in 0, 1. Okay, and what you assume is that in the interior of this flow box, you don't have any periodic orbit, and you have one orbit that is being trapped. Okay, so there's one orbit coming from below, and that is somehow being trapped in this flow box here. Okay, and this is what is called a trap. And then a plug is something stronger because it also asks to satisfy some entry-exit matching condition. So this means that if it enters from below, it leaves exactly the same position from above, basically. Okay. So why is such a construction good for? Well, such a construction is good for because if you have a plug, okay, you can destroy a finite number of periodic orbits. Okay, because the periodic orbits, you can just put like one of those flow box here, and you can destroy one by one those periodic orbits. Okay, so this is what are traps and plugs, and those have been studied a lot in contact geometry. So by the Weinstein conjecture, there cannot be plugs. Okay, because if there was a plug, okay, you could find counterexamples to the Weinstein conjecture, but the Weinstein conjecture is known to be true in many cases. Okay, so there cannot be plugs. Okay, and the existence of traps is much more subtle because in dimension 3, in fact, it was proved that there are also no traps. This was proved by Eschberg and Hofer, and then they conjectured that there would not exist any traps in higher dimensions, and this was only proved, well, kind of recently, 5 years ago, by Geiges, Röttgen, and Semisch, that that traps in fact do exist in higher dimensions. Okay, and of course, if we ask this for in the setup of B contact geometry, this is a new question because this vector field needs to satisfy the property of being the Rip vector field associated to a B contact form. And so, first result that I'm putting here that I proved with Eva is that there exist traps for the BM Rip flow. Okay. In this talk, there won't be any proofs, but there will be 2 proofs, and those are proofs by pictures. Okay, so this is first proof by picture. So you have here a flow box. Okay, this is our flow box in 3 dimensions. So at the boundary of this flow box, you have the linear flow. Okay, and in the interior of this flow box, you have the critical set a 2 sphere here. Okay, and the Rip vector field on this two sphere just gives you rotation, okay? So you have here rotation, okay? And you have one orbit that enters here, that goes to a singular point here. So this is an orbit that is being trapped because at this point here, the Rip vector field is vanishing, okay? And on this sphere here, you have rotation. On the boundary of this sphere, or on the neighborhood of this sphere here, you have rotation, okay? And this is in fact a trap, but not a plug, because if you enter here, you don't leave here again, but you leave at a different exit point, okay? And this is somehow not good enough to prove non-existent result of periodic orbits, because even though you may kill one periodic orbit here, you may create new ones here. So you really create some new dynamics here. So this is not good enough to prove counterexamples for a periodic orbit results, okay? So the question that I raise here is about the existence or maybe non-existence of periodic orbits on the contact manifolds. And as you see here, there's basically two different behaviors, because on the critical set here we have infinitely many periodic orbits, okay? Because like all the orbits here are periodic, okay? And so there are two different, there's the question of existence and non-existence, but there's also the questions of dynamics on the critical set and away from the critical set, okay? And in fact, this behavior on the critical set is really something that happens in dimensions in dimension 3 always. So if you have a BM contact manifold of dimension 3, okay, then the restriction of this Rip vector field is in fact Hamiltonian, okay? And this really is three-dimensional. This is not something that happens in higher dimensions, okay? And what we proved is that in fact in dimension 3, if the critical set is compact, okay, it's closed, so compact without boundary, then there exist infinitely many periodic Rip orbits on the critical set. And so this is really what we saw in this picture here, that we have infinitely many periodic Rip orbits, okay? And this is really because it's a Hamiltonian vector field, okay? And so this means that in the three-dimensional case, you always have infinitely many periodic orbits on the critical set. Okay, so the question on a periodic orbit away from the critical set is a different one, and so it's fairly easy to produce, in fact, some examples that have infinitely many periodic orbits on the critical set, as we saw is always true by the last result, but that have none of them away from this critical set. Okay, and this is for instance, an example is given by the 3-sphere, and this, so as a 3-sphere, this sits into this b-symplectic manifold here, okay? And you have a Liouville vector field that's transverse to that 3-sphere, okay? And the induced Rip vector field gives you rotation on the 2-sphere, but it's very easy to check that this is in fact has no periodic orbits away from this away from the critical set. Okay, so this means that on one hand you always have periodic orbits on the critical set, but you may not have periodic orbits away from the critical set. And now what I want to talk about is one existent result where you can assure that there are periodic orbits away from the critical set, and then like we'll try to apply this to the initial problem of the restricted free-body problem. So let me give you a definition that is well known for people in contact topology, which is a contact manifold that's over-twisted. So contact manifold that's over-twisted means that there exists a two-disk in this three-dimensional manifold, such that so what you can do, you can take the tangent space at a point of the disk and intersecting the kernel of the contact form, okay? And this defines a one-dimensional singular foliation, okay? And if this one-dimensional singular foliation looks like this, okay, we say that this three-dimensional manifold is over-twisted. So this here is an over-twisted disk, okay? And so this is an object that has been studied a lot in contact topology, and one of the reasons for this to be studied a lot is, well, I mean, there are several reasons, but let's say like this result is a very classical result from '93 by Hofer that tells you that if the three-manifold is a contact three-manifold, so for a fixed contact form here is over-twisted, then there exists in fact a periodic orbit for the Rip vector field of this contact form here. Okay, and so the proof of this is using results on the symplectization of this contact manifold, and so this is something that is true for closed manifolds, but is of course not true for open over-twisted contact manifolds. Okay, and what we'll see is that the result of this theorem can in fact be adopted to the setting of the contact manifolds. This is kind of surprising, let's say, because we somehow tackle with non-compactness as well due to the singularity. So what we need is two ingredients. Well, we need one ingredient that is over-twistedness. So we say that the BM contact manifold is over-twisted if there exists an over-twisted disk away from the critical hypersurface. So away from the critical hypersurface, everything is of course smooth contact. So this is what we call an over-twisted BM contact manifold. And second ingredient is something that we need to control this non-compactness issues that we in fact have. Okay, so a contact form is called R+ invariant around the critical set if there exists a strict contact vector field. Okay, so this is a vector field such that the Lie derivative of this is 0. Okay, and this implies in fact that the contact form writes down as u dz over z to the power of m plus beta, where u is a smooth function on z and b is a smooth one form on z. So we have kind of a decomposition here. Okay, and so because of this R invariance, in fact, what we're able to prove is that there's some duality happening, and this is the following. So if you have a closed BM contact manifold and you have an over-twisted disk away from this critical set, okay, there are two different options. There's either the options that there exists a periodic orbit away from the critical set, or there's a one-parametric family of periodic orbits approaching the critical set. Okay. And so, as I told you, this is an adaptation of Hofer's technique in this setup. I'm going to do another proof by picture of this theorem here. And one question that I want to raise, and I think this is a very interesting question, is because this theorem, in fact, we deduce it for more general theorems. So this is a corollary of a more general theorem for open contact manifolds. So because of this R+ invariance, we're somehow able to control this non-compactness issues that you run into in general. Okay, so this is a question that I think it's very interesting to see if you can find other application of this R+ invariance, in fact. And the proof by picture is the following, is that here you have an over-twisted disk, and out of this over-twisted disk, what you can produce a Bishop family, which is a family of pseudo-homomorphic disks, and then some bubbling argument tells you that, in fact, bubbling is happening in the interior of this Bishop family, okay? And there are basically two possibilities where this Bishop family can blow up. Either it blows up in the interior away from the critical set. So this is not what is happening here in the picture. All this Bishop family blows up, in fact, close to the critical set. And then like this R+ invariance is used to somehow push this Bishop family back so that it doesn't touch the critical set. And this is also where you get like this one parametric family. Okay, so this is all the result that I wanted to talk about, the dynamical result of those big contact manifolds. So let me very briefly, because I see that I'm running out of time, go back to the initial motivating example. So the initial motivating example was the restricted three-body problem. And so what we can do here is that we can in fact find a Liouville vector field that is another Liouville vector field that is transversed to this level set here. Okay, and the nice thing is that this Liouville vector field, in fact, remains Liouville vector field after the McDehee change of coordinates. Okay, so you have a Liouville vector field that is transversed to the level set of this Hamiltonian. Okay, for this B3 symplectic form, in fact. Okay, and due to this, we can in fact prove that in this restricted three-body problem that there are we can prove that this is really a B3 contact manifold, and that there exists in fact infinitely many periodic orbits on the critical set. Somehow this number of infinitely many periodic orbits doesn't follow from the result that we mentioned before. This is something that you really need to compute by hand, because the critical set is a non-compact cylinder. So the result that I was mentioning before doesn't apply here. But still, like direct computation imply that the reflector field has in fact infinitely many periodic, non-trivial periodic orbits on the critical set. Okay, so this gives rise to many periodic orbits on the critical set. So this is a manifold that in the initial problem is the manifold in infinity. So so now to finish off my talk, let me raise one question: is that like, can those periodic orbits that are contained in the manifold at infinity, can those in fact be continued away from the critical set? So this is something that we're trying to prove, is that in fact, like if you have some periodic orbit on the critical set, so this is what is here in red, okay, that those periodic orbits can in fact be continued away from this critical set. And what we think is that because of this examples where there are no periodic orbits on this on the B3 on the B contact manifold, what we need to consider is in fact a more general notion of periodic orbits, and those are singular, what we call singular periodic orbits, are also, well, I mean, as a dynamical system group, those would call them rather heteroclinic orbits. So what we conjecture is that for a B contact manifold, there exists in fact always, in the compact case, there exists in fact always a singular periodic wave orbit. And this is something where we have done some recent progress with Daniel Peralta-Sal from Ethermat, where we think we'll be able to prove that generically this conjecture is in fact true. I didn't tell you what generically here means, because this is still work in progress, so I won't go very much into detail about this, but we'll only state it like this. Okay, so
we can. Oh well,
all
okay.
All that I wanted to talk about. Okay, well, here you have some the bibliography. So thank you very much for your attention, all of you.